Welcome to Empowered Learning. This is the second video in the video series for the cross product operation. So in video number one, if you're running across this video and you want to know what video number one was about, it was setting the foundation for the thinking behind what the cross product function or cross product operation is, the things that we need to take into account that kind of go along with how vectors act inherently to capture the rotational effect that happens whenever a vector acts on another vector where both of those vectors are in the same plane. What this video is for more practical application of the cross product. So we will actually go into what the cross product is defined to be. And I won't do a proof on that. And that will actually be the third video, kind of giving you the background as to why we're able to say the cross product is what it is. But we'll state what it is, see some uses of the cross product, and then do several examples. And that will be the focus of this video. And again, the last video in this series will be about doing things like proving, for instance, how I can actually say that the cross product is this, and how we're going to look at the cross product in its determinant form and show how that could actually be written the way that it is as well. Okay. All right. So let's say we have vectors u and v that are going to be in 3D space such that we could write them in this form here. And I'm just using the fundamental unit vectors I, j, and k to write it in components, but algebraically speaking. And of course, the U1 through U3, V1 through V3 are all scalar quantities. Now, just for simplicity here, I'm also going to say, let's assume that we have some vector W, because I actually defined this later on, but I should have probably just done it up here. So I'm going to go ahead and write it now. So I also want to define another vector W where all three of these are going to be scalar quantities as well. And so another way of saying that is that W1 through W3 would just be real numbers. So if we're considering all that, then we say that the cross product of U and V, we denote it as this, and we say U cross V can be found one of two ways. And so the first way that we define it is in terms of sign function here. And so we say U cross V is going to be the product of the magnitude of both vectors U and V times sine theta. And this takes care of the magnitude part of this pseudo vector. And go back to video number one if you don't know what I mean by a pseudo vector. And then that's multiplied times some normal vector. And of course, what this vector is going to be, it's going to be a unit vector, or a vector that describes the direction of U cross V. And it's going to be perpendicular to the plane that both U and V are in. Okay. So we also know that theta is going to be, and I put this word in here, the smallest angle between U and V. And I say that because we want to make sure that the angle in between vectors U and V is going to be between 0 and 180 degrees. Okay. And so for instance, if I had some vector U like this, and let's say I had a vector V like this, then matter of fact, let me make this, I'm going to draw this differently to make the angles easy. So let's say this is U and that's V. Okay. Now, of course, we know that there's a 90-degree angle in between here, but there's also a 270-degree angle. And of course, we want to consider the smallest one. Okay. Not the largest one. So that's why I have that word smallest there. All right. Again, U and V are in the same plane, and in hat, as I call it here, is going to be a pseudo vector that's going to be perpendicular to the plane that both vectors U and V lie in, and the magnitude of that vector is going to be 1. And that's what makes it a unit vector. Now, the other way that we can calculate the cross product of u and v is in determinant form. And of course, if we had some matrix with I, J, K, u1 through u3 and v1 through v3, we would just take the determinant of that. And of course, in taking the determinant of it, this would be like taking the determinant of a 3x3 matrix. We would essentially say that we're going to take I times, and then we would get rid of this row and this column, and we would do the determinant of this minor matrix here. And so that's how we get this first term. And so for the second term, we would do minus, and of course the formula for taking the determinant here, we say plus, minus, plus. So we would say a positive I times what I just said here, and then this will be minus, and then j, and then we would cross out this column, cross out that row, and then we would take the determinant of the minor of u1, u3, v1, v3, which would just be u1 times v3 minus v1 times u3. And so that's what we have here. And then lastly, we would add and then multiply times the vector k. We take out this row and that column, and we would take the determinant of this minor matrix, which is u1, u2, v1, v2. And to take the determinant, we just say u1 times v2 minus v1 times u2. And that's how we get this result here. And of course, if this is what the corresponding pseudo vector u cross v is going to be, then its magnitude would just be the sum of all the square of its components, and then we take the square root. Okay. All right. So now that we've defined what u cross v actually is in two different ways, now we want to talk about some common uses of the cross product. Probably the most common use of the cross product is to find the magnitude of some vector that's going to be perpendicular to these two other vectors, where both of these vectors lie in the same plane. Okay, and this is solely to figure out if we're thinking about it from a rotational standpoint. And I'm going to use the analogy of we have a force U acting on V for a screw, and we're trying to screw screw into, let's say, some wood or whatnot. The magnitude of our cross product would be, all right, well, for instance, how fast is the screw screwing into the wood, or with what force is the screw screwing into the wood? Okay. So, now, notice here that in taking the magnitude of n hat, or the unit vector for the cross product here, well, not necessarily the unit vector for the cross product, but just a unit vector in general, it is going to be 1. Okay. And of course, we see that the magnitude of the cross product is just going to be the product of the magnitudes times sine theta, where again, theta is assumed to be in between 0 and pi, or if you want to do it in degrees, in between 0 and 180 degrees. Another thing that we could use a cross product for, but I probably wouldn't recommend it, but technically you could do this, is to find the smallest angle in between vectors u and v. Okay. Now, if we used this formula to do that, of course, we would have to do the magnitude of u cross v, and then rearrange this to solve for theta. And of course, you see this is what this looks like. Okay. Now, the issue here is that notice that my theta here is defined as a piecewise function because of how the inverse of the sine function acts. And of course, sine inverse is technically only defined in quadrants 1 and 4, but our angles that we need to consider will be in either quadrants 1 or 2. So we have to sort of use reference angles to help us to be able to figure out what angles in quadrant 2 would look like. And so that's what this piece is for. Now, my note that's down here is that I would recommend that you use this form of finding the angle in between two vectors, because number one, doing the dot product of u and v is much easier to do. And number two, the arc cosine or cosine inverse function automatically takes into account what quadrant you're in based upon the sign of this particular expression, okay? And so I go into detail on that there. So we also have an alternative formula in terms of vectors to talk about the area of a parallelogram. And essentially, a parallelogram is just four-sided figure like what you're seeing here. The most simple parallelogram that you know is a square, okay? But rectangles are also considered to be parallelograms as well. Of course, what makes a parallelogram is that you have figure to where all the sides are parallel to another side, okay? So that's pretty much it. And we see here that if we're looking at the height of this particular parallelogram from the tip of this vector down to vector u, of course, it's going to be perpendicular. Then we know that anytime we look at an angle, the side across from it, if let's say the length of this was 1, would be considered sine of an angle. But since it's v, then of course we consider the magnitude of v, and that's hence why we have this here. Yeah. We can also find the area of a triangle. I put oblique triangle here because that's normally what we use it for, but it could be really any triangle. And essentially, if the area of a parallelogram is just going to be the magnitude of u cross v, then half of that is going to be the area of a triangle. And of course, we would have to know what these points A, B, and C are and formulate our vectors u and v in terms of what that directed line segment AB and AC would look like. Another application would be to find the torque vector magnitude and direction. So whenever we're trying to screw something, like I've been using analogies before, so we have this this wrench here and we're trying to screw in this bolt. Note that the force in which we press down on this wrench, there's a portion of that which is going to be perpendicular to the point where we apply perpendicular to the wrench, that is, that's actually going to be the actual force that's going to contribute to the rotational effects that happen to make this bolt screw into whatever it is we're trying to screw it into, okay? Now, as far as the formula, the torque vector is just simply the radius vector, and of course that's just the distance from here to here, and we can look at that radius as a vector since it is a length in a certain direction. Of course, the force that we apply on the tail end of the wrench here, we can look at the magnitude of that, and of course sine theta, because again, we're trying to capture the rotational effects, and we've already said that sine of some angle being in the mix here would actually make sense for cross product. So and of course here we have this unit vector here, okay? Now, another way that we could express this is just simply as R cross F, okay? And of course, R cross F, if we write it out, it's going to look like that. So continuing on, we could also find the volume of a parallelepiped, which is basically a real fancy word for a box. But of course, the box, just like the four-sided figure that we saw earlier, it could be slanted. And so we know that the volume of a parallelepiped, or volume of a box, is just going to be the area of the base times the height. And we can talk about the area of the base just being the magnitude of u cross v, and the height here could be the magnitude of w cosine. And so you see here where we're talking about the height of the parallelepiped. And that's why we have the magnitude of W cosine theta. And again, here's where I talk about defining the vector W, but we've already done it before, so we don't have to worry about that again. And last but not least, we can use what's called the triple scalar product as a determinant to also find the volume of a parallelepiped. And all we really need to know is what are the components of vectors u, v, and w. And so notice that this outcome will actually be a scalar quantity because of the fact that u cross v here is a vector, and I'll just call it, let's say, some vector A. And we're taking a vector W and we're dotting it with a vector A. And we know that whenever we do the dot product, we end up with a scalar quantity. And so that's why this particular result actually ends up being a scalar quantity, and it makes sense for us because of the fact that we actually need a real number value here, okay? And so we could actually use this to be able to basically find out what's going to be the volume of a parallelepiped. And in this case, we would just take the magnitude of u cross v dot w to find it. And we only do that because of the fact that sometimes whenever we do these determinants, we may end up with a negative number. And of course, having negative volume for a box in this case doesn't make sense. All right, so now let's get into doing some examples here. So for our first example, we want to find the length and direction when what we're trying to find can actually be defined of the pseudovector u cross v and pseudovector v cross u. Now, if we're given that our vector u is the vector that's going to be perpendicular to the unit vectors I and j, if you remember, we kind of made this little chart earlier to kind of guide us, and I'll recreate it here. And so kind of said like this. And so this lets us know that here that I cross j, if I go I cross j, then what comes after that is k. So all this is just going to be the vector k. And again, we know that the unit vector k, which is the unit vector for the z axis, is perpendicular to both the vector I and the vector j. And of course, it's going to be perpendicular to the plane that they're both in as well. All right, so if vector v is j cross k, then of course that result here is going to be the vector I. And so in looking at that, we know that if u cross v is just going to be the same as k cross I, and of course k cross I will just give us j. And so this would be the actual vector here. So what we want to do is find the length and direction. So by definition, we know that this vector here in component form is just going to be this. So which is a unit vector, because if we took the magnitude of this, we would see that it's 1. So that would be the actual length. And of course, in the direction, j would be its own direction because it is a unit vector. Okay. All right. So our answer here is length. It is going to be 1, and our direction is going to be j. All right. So let's move on to example number 2. So with example number 2 here, I'm going to write this in component form just to make doing the computation here a bit more concise. Okay, so this is what our u vector is, and 2, 2, 1 is going to be what our v vector will be. And so what we want to do is find out what u cross v is, and then afterwards figure out its length and direction. So for starters here, we don't necessarily know what the angle is in between these two vectors. So although we could use this form of what the cross product is, to do that, we would have to do more work than what's necessary, because of the fact that we would have to figure out what the angle in between those two vectors is by actually doing the dot product here, doing all this business, okay? And we really don't want to do all of that, okay? Because of the fact that we could write u cross v in its determinant form, this allows us to be able to do what we need to do here in finding out what u cross v is without necessarily knowing the angle in between the two vectors. And so this is the route that we want to go, okay? So I'm saying all this that for this example, since we just have the two vectors, we don't want to use this version of the cross product because we don't want to have to go through all of this, okay? All right, so with that, let's go ahead and set up our determinant here. And of course, we'll write all of the u components first, and then the v components second, okay? And from here is just doing determinants. So I'm going to write this out. So we'll say I times, and when I do this, this particular row and this column are going to go. So what's going to be left is I'm going to do the determinant of this minor matrix here, minus j. And then for here, what I do is the row and the column that have j in it, I get rid of those. And all I have left is the minor with -8, -4, 2, and 1. And then I do times k, or plus k times, take out the column and the row with k in it, and I'm left with the minor matrix -8, -2, 2, 2. And so now we go into calculating what we'll get here. And so the determinant of these minor matrices is just going to, we're just going to cross here. So -2 times a +1 will give me a -2. And then we subtract 2 times a -4, which is -8. Okay. And then we repeat for these other two minor matrices. So we have a -8, because -8 times +1 minus 2 times -4, which should be -8. And then we finish up with k. So -8 times 2 is a -16, minus 2 times 2 is a -4. So from here, plus a -8 is the same as adding 8. So -2 plus 8 is +6, minus j times. And here, -8 plus 8 is going to give me 0. And then plus k, and subtract the negative is the same as addition. -16 plus 4 is a -12. And so this just ends up being 6i minus 12k, not j. Okay, so this is what our pseudo vector u cross v is going to look like here. Okay, so now that we know what that is, what we can do is figure out what its length, mainly the magnitude of this vector is, and its direction. Okay, so I'm going to switch colors for that. So now that we have that, the magnitude of u cross v is just going to be square root of the sum of the components squared. Okay, so this is square root of 36 plus 144, and that's going to be square root of 180. And square root of 180, that's the same as 180 is same as 20 times 9. So that would be square root of 9 times 10 times 2. Or, yeah, and I actually got a 2 times 5 here, yeah. So we could rewrite this as 10 times 2 is 4 times 5. And of course, this could be rewritten this way. That 5 didn't come out real nice. And essentially here we know that square root of 9 is 3, square root of 4 is 2, so 3 times 2 is 6. And this will be our length. Okay. So now that we have the length, we can now talk about the direction. And so the direction is just going to be the unit vector. And essentially this is just 6i minus 12k, all that divided by 6 times square root of 5. And if we rewrite that, that is just going to be 1 over square root of 5 in the I direction minus 2 over square root of 5 in the k direction. And so this would be the direction of u cross v, and this would be the length of it. Okay, so we could essentially just rewrite u cross v as 6 times square root of 5, and then just rewrite all of this in here. Okay, and so mainly whenever you get those questions of, hey, express your vector in terms of length and direction, it's mainly because they want you to rewrite it this way. Even though we're not asked to do that in this problem, that's really the purpose for it. All right, so let's move forward here. So for our next example, it'll be kind of the same thing. We will say this vector here, we'll go ahead and write it in component form to make the math a little easier to do. So for vector u, we have the components 3 halves, negative 1 half, 1. And then for vector v, we have 1, 1, 2. So again, since we don't have the angle in between these two vectors explicitly known, we're going to use the determinant form of the cross product to be able to figure out what this pseudo vector will be. So say that u cross v is going to be, and we will do this determinant here, 3 halves minus 1 half, 1, and then 1, 1, 2. And for this one, I'm not going to do all of the middle calculations like how I did before, because I'm thinking that once I did that, you kind of saw what was going on here. All right, so we have vector I, and we're going to get rid of the row in the column with I in it. And so we just focus on this minor here. So we got negative 1 half times 2, which is a minus 1. Minus 1 times 1 is 1. Okay. And we do the same thing with j. Get rid of the corresponding column and row with j in it. And then we just look at what's left. 3/2 times 2 is 3, minus 1 times 1 is 1. And then plus k, get rid of the column in the row with k in it. And we look at what's left, and we just have 3/2 times 1, which is 3/2, minus 1 times a negative 1/2, which would be a negative 1/2, and a negative times a negative would be a positive. And if we simplify all that, that would be a minus 2i, looks like minus 2j, and a plus 2k. So that is what our u cross v vector will be. Now, if I want to know the length of, or the magnitude of this vector, then I just take square root of the sum of all the squares of its components. And so that is, well, let me write that over again because that didn't quite do what I wanted it to do here. All right, so I have negative 2 squared plus another negative 2 squared plus positive 2 squared. And of course, each of those terms are going to end up being 4. So 4 plus 4 plus 4 is 12. And we can break this down to square root of 4 times square root of 3, which will just end up being 2 times square root of 3. So that will be our length. Of u cross v. So now that we have that, then of course we can find the direction, aka the unit vector for u cross v, which will just be u cross v divided by its magnitude. And if we look here, that's minus 2i minus 2j plus 2k, all that divided by 2 times square root of 3. And this ends up being a minus 1 over square root of 3 I minus 1 over square root of 3 j, and plus 1 divided by square root of 3 k. And that is what our direction of u cross v turns out to be. All right, so we have one more example of this type, and then we will move on to example number 2. So just want to rewrite that, make that look better. All right, so for this last example here, notice that this example is going to be real simple, because whenever I look at u cross v and noting that my vector v is 0, doesn't matter what this ends up being, we know that it's going to turn out to be the 0 vector. So I don't care what u actually is. If I cross it with the 0 vector, it's just going to end up being the 0 vector no matter what. Okay. So with that being said, we know that the length of the 0 vector is going to be 0. And if we start talking about the direction, this is going to be undefined. And the reason why it's undefined is, remember that the direction of a vector, or its corresponding unit vector, is going to be its vector divided by the magnitude. And essentially you have the 0 vector divided by a scalar value of 0. And by definition, this is undefined. Okay. So that's what we meant. And I'm going to go back to the beginning of this particular example to show you what I mean here. So in our instructions, when we said find the length and direction when defined, that was one of the reasons why we said when defined, because in our situation like example 1D, we see that, of course, the direction can't be defined because we're taking a number and dividing it by 0. All right, so let's move on to example 2. All right, so for example 2, we're asked to sketch the coordinate axes and then include our vectors u, v, and u cross v in it as vectors starting at the origin. Okay, so here, let's go ahead and set that up right now. I'm going to let this point be the origin here. And so because of that, I'm going to let that be the positive x-axis. I'm going to let this be the positive y-axis. And I'm going to let this here be the positive z-axis. Okay. All right. So with that, we want to sketch a graph of the vectors u, v, and u cross v. Okay. Now, of course, vector u, if we look at this in component form, it's just 2, -1, 0. Vector v is going to be 1, 2, 0. And of course, u cross v, again, since we don't know the angle in between the two vectors, we'll just use the determinant form of it to figure out what it's going to be here. Okay. And doing this for the I vector, I'm actually going to move this down so that I can have a little bit more room here. So for the I vector, I get rid of this column and this row, and I just have -1 times 0 minus 2 times 0, and that's just 0, minus j, get rid of the middle row in the top, the middle column in the top row. And so again, that's 2 times 0, which is 0, minus 1 times 0, which is 0. And then plus k, get rid of this row and this column. And actually, I could have just, did what I'm doing now, and that's it. But I'm kind of wanting to stay with the general form here. So if I do that, then I have 2 times 2, which is 4, minus 1 times a -1, which is a -1 here. And all of this just ends up being positive 5 times the unit vector k. So if we were to graph each of these vectors here, I'm going to go ahead and graph vector u in blue. So starting from here, I'm going to graph this to where each division is like half of a unit. So this would look a little longer. So I'm going to have, in the x direction, I'm going to have half unit 1, half unit 2. So basically 1, 2, 3, 4. And then I need to go in the y direction, -1 unit, which would be here. I'm kind of losing my, these lines are really messing with me. So let me zoom in a little bit here. So I got 1, 2, 3, 4, and then I got 1, 2 here, and that's it. So that would be the terminating point for vector u. Go ahead and draw that. So for v, I'm going to go 1 in the x direction, which would be 1, 2 units here, 2 in the y, so 2, 4, and then 0 in the z direction. So this is vector u. So we got vector u here. Got that. That's vector v. And I'm going to use vector k in a different color. And so, vector u cross v, which is 5k, will be in this direction here. So we're going to go up, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll put the terminal point here, be like that. Not sure what's happening, but this is what my vector 5 K is going to look like. And so that is what a drawing of the vector u, the vector v, and u cross v will look like. All right, so let's look at another example. All right, so for our next example here, we have a vector u, which if we put this in component form will be 0, 1, 2. And of course, our vector v is the same as the fundamental unit vector I, which will be 1, 0, 0. Okay. Now, if we do u cross v, of course, we can use the determinant form for this. And we'll have 0, 1, 2, and then 1, 0, 0. And again, for here, I could technically just look here and take out this row, take out this column, take out this row, and then just do this minor here. But I want to stay with the normal convention for how we do this, just in case people that are watching this video may not be familiar with determinants. So I'm going to keep it pretty standard here. So we'll say I times, take out this column, take out this row, and then 1 times 0 is 0, minus 0 times 2 is 0. Okay, minus j, take out middle column and top row, 0 times 0 is 0, minus 1 times 2, which will be a minus 2, and then plus k. Take out last column, top row. I'll have 0 times 0 is 0, minus 1 times 1, which is a minus 1. And this result will give us just 2j minus k. And so therefore, u cross v in component form will just look like 0, 2, minus 1. And so if I was to go ahead and draw the vector u, that would be 0 in the x direction, but 1 unit in the y direction, and then 2 in the z. And so remember, I'm doing half units here. So this is what my vector u would look like. For our vector v, that would just be the fundamental direction vector for the x-axis. So we're just going to go to this point here, and that would be the vector for I. And then of course, we'll do this in a different color. I will do it in red this time. U cross v will be 0, 2, negative 1. So 0 in the x direction, 2, 1, let's see, 1, 2 in the y direction, and then here in the z direction. All right, and so this will be where u cross v will be, and we will just connect that vector there. So that's what that would look like. And of course, remember that our vector u and our vector v, which is in this case the unit vector I, both of those are assumed to be in the same plane, and that vector u cross v is assumed to be a vector that's perpendicular to the plane that both vector u and vector v, which is equal to vector I, is in. All right, so let's move on to example number 3. All right, so for our next example here, for each set of points that's given to us, we want to find the area of the triangle that's determined by these 3 points. And we also want to find a unit vector that is going to be perpendicular to the plane that this triangle is going to be lying in. Okay, so for example 3a, we need to form a triangle out of these 3 points here. So we'll let our point P, which is the point 1, -1, 2, be here. We'll say Q is down here, and this will be the point 2, 0, -1, and we'll say about right here is R, which is 0, 2, 1. And if we connect these, we'll see that we have a triangle here. Now, in order for us to find the area of this triangle, one of the things that we have to remember here is that the area is 1/2 of the cross product in between two sides of our triangle, interpreted as vectors. And so I am going to use, let's see, point P as sort of the point that both vectors originate at that I'm going to create. So because of that, I am going to be doing 1/2 of the magnitude of vector PQ cross PR. Okay. So again, in this case, since we are not given what the angle in between vector PQ and vector PR is, we're going to use the determinant form of the cross product to be able to calculate it. Before we do that, though, we need to actually state what our actual vectors will be here. So we'll see that for our vector PQ, we're just going to take the difference in components here. So if we do go from P to Q, so 2 minus 1 will give you 1. So our vector PQ here in the component form will just be 2 minus 1, which is 1, 0 minus a -1, which is 1, and -1 minus 2, which will be -3. Our vector PR, we go from R back to P, so 0 minus 1 is a -1, 2 minus a -1 is going to be a +3, and 1 minus 2 is a -1. And let's fix that negative that's there. All right, so now that we have these vectors here, we can go ahead and figure out what this cross product is going to be. So we'll have PQ cross PR, and we're just going to do the determinant. And we'll have 1, 1, -3, and -1, 3, -1. And in the I direction, get rid of the first column in the top row. And we'll just have 1 times a -1, which is a -1, minus 3 times a -3, which would be a +9. Then minus J. Take out the middle column in the top row. 1 times a -1 will give us -1, minus -1 times a -3. Of course, the negative times the negative is a positive, but we still had a minus there, so that will give us -3 here. And then plus K. Take out the last column, top row. 1 times 3 is 3, and minus -1 times 1 is a -1, and negative times a negative is a positive. And so all this just ends up equaling 8i, and that looks like -4 times negative, so it's going to be +4j, and plus 4k. So that is what our cross product pseudo vector will be. So now to find the area, we need the magnitude of this vector and then take half of it. So let's find the magnitude first. So to find the magnitude, we just take the square root of 8 squared plus 4 squared plus another 4 squared. And that will be basically 64 plus 16 plus 16. 16 plus 16 is 32. So 64 plus 32, that will give us 96. So this will be square root of 96 here. All right, so let's get rid of this. And of course, 96 is just 16 times 6. So we could rewrite this as square root of 16 times square root of 6. And of course, square root of 16 is 4. So this just ends up being 4 times square root of 6 as the magnitude of our cross product. And so therefore, the area of the triangle here will be just 1/2 of whatever this magnitude is. Which would just be 2 times square root of 6. And the other thing that we want to find out is what is going to be the unit vector that's perpendicular to this plane that has this triangle in it. So I'll just call this V. So we'll say this unit vector V here is just going to be the cross product divided by the magnitude of the cross product. Of course, in the denominator, our cross product magnitude is just 4 times square root of 6. In the numerator, we have 8i plus 4j plus another 4k. And once we simplify, we'll just have 2 times square root of 6 in the I direction plus 1 divided by square root of 6 in the j direction plus another 1 divided by square root of 6 in the k direction. So this would be the vector that we're looking for that's going to be perpendicular to the plane that has a triangle PQR. All right, so if we go back here and look at our answers, oh, and I forgot to write this too. So since this is an area, this should be square units. Need to mention that. So here, this is the answer for our area of our triangle here. And the unit vector is going to be perpendicular to this particular, the plane that the triangle is in. This would be the answer to that question. All right, so let's look at part B of this example. All right, so for our second example, we want to do the same thing. So the first thing that we want to do is kind of get an idea of what this particular triangle is going to look like. So I'm just going to come here, and this will end up being point P, which would be -2, 2, 0. And I'm going to put R down here. And this will be a -1, 2, -2. And Q will be somewhere up here. And we will label this. Let me put the point first. So this will be the point 0, 1, -1. And this is Q. And so now we'll just connect all these. That is our triangle. And so now we just need to define our vectors PQ and PR again. And so just like how we did last time, I'm going to use this point P here as the point that both vectors, where both vectors have its initial point from. So if I do that, then let's see our vector PQ. If we look here, we go from Q back to P. So 0 minus a negative 2 is going to be a positive 2. And let's make that 2 look a little better. We have 1 minus 2 gives us a negative 1. And a negative 1 minus 0 gives us a negative 1. All right, so now let's figure out what the vector PR is going to be. So we go from R back to P. So negative 1 minus a negative 2 is the same as negative 1 plus 2, which will give us a 1. 2 minus 2 gives us 0. And here a negative 2 minus 0 gives us a minus 2 here. All right, so now that we have those two vectors, we can go ahead and calculate the cross product of both of them. And again, we'll do the determinant form because we don't have the angle in between the two vectors, and we don't want to go through all that work to figure out what it is. It's really not necessary. So put the components down for the PQ vector and then the PR vector. Then we just calculate the determinant. So this will be I times, take out this first column, top row, negative 1 times a negative 2, which is 2, minus 0 times whatever, give me 0, minus J, take out the middle column and top row, 2 times a negative 2 is a minus 4, minus 1 times a negative 1, which is a negative 1, so that will make this plus here. And then K, take out the last column, top row, 2 times 0 is 0, minus 1 times a negative 1, which is a negative 1. So minus a negative is the same as addition. And this result here ends up being 2I plus 3J, because the negative times a negative is a positive, plus K. And so now that we have that, we can now find out what the magnitude of this cross product is. So we can use that to find both the area of this triangle here, as well as find a unit vector for the cross product, which will essentially be a unit that's going to be perpendicular to the plane that this triangle is in. So to take the magnitude of this, we just do square root of, and we just take the sum of the square of all the components. And here we have 4 plus 9 plus 1. So 4 plus 9 is 13, plus 1 is 14. So that is just square root of 14 there. And I'll kind of write that a little bit more compact. All right, so now that we have that, we know that the area of our triangle PQR is just going to be 1/2 of the magnitude of this cross product pseudo vector, and that's just going to be square root of 14 over 2 square units. And finally, again, if we let V be the vector that's going to be perpendicular to the plane that has this triangle in it, then here we can essentially just say that we do the cross product over the magnitude of the cross product of PQ and QR, PQ and PR rather. Then here this would just be 2I plus 3J plus K for the cross product, and then divide that by square root of 14. Okay. All right, so here this will be 2 divided by square root of 14 in the I direction, plus 3 over square root of 14 in the J direction, plus 1 over square root of 14 in the K direction. And I could work on simplifying this a little bit more. I know that, was it 2 divided by square root of 14? That's going to be the same as square root of 2 times square root of 2 over square root of 2 times square root of 7. So if I really wanted to deal with that, this would reduce to 1. And then if I rationalize the denominator here, this would just end up being square root of 14 all over 7. So I could rewrite 2 times square root of 14 as just square root of 14 over 7. But for the trouble, I'm just going to keep it the way that it is. So we're just going to go with this particular answer for the unit vector perpendicular to the plane with this in it. And of course, the length or the magnitude of our cross product is this. Of course, half of that will be the area of this particular triangle. Okay, so for example 4, I've broken this up into 2 parts, and I've already worked this one out because it's a lot going on with it, but we've kind of done enough with calculating the cross product of 2 vectors to where we can kind of go through these examples a little bit more efficient at this point. So what we want to do is basically verify this property here. And what this is are the different forms of the triple scalar product. And so essentially what we're trying to show here is that since this result that we're looking at here is going to end up being a scalar in every case, then no matter how we switch these around as far as the vectors are concerned, is all going to equal to the same thing. Okay. So we see here, for example, A, the 3 vectors that are given to us are this vector I minus j plus k, vector V, which is 2i plus j minus 2k, and W, which is minus I plus 2j minus k. And of course, I've written the component forms for those. And then since here I need to find out what U cross V is, V cross W, and W cross U is, I go ahead and do the determinant calculation for each of those cross product pseudo vectors. And you see that I get I plus 2j plus 3k for U cross V, V cross W, we get 3i plus 4j plus 5k, and W cross U ends up being just I minus K. And so I've written that into component form to make life a little easy for me. So once I know what those resulting vectors are, all I have to do is perform the dot product with it, with what it tells me here. So U cross V, I need to dot it with W, V cross W, dot it with U, and W cross U dotted with V. So the one letter out of U, V, and W that it doesn't have, that's what you dot it with. Okay. And of course, you see that when I do the dot product with each of these, we see that we end up getting 4 each time, which is essentially what it is that we were trying to show. Okay. That since the triple scalar, since it ends up being the triple scalar product ends up being a scalar quantity, no matter how we situate the vectors, still going to end up being the same thing. Now for example B, kind of the same thing, just have different vectors that we're dealing with. And of course, we write u, v, and w in component form. We go ahead and do the cross product via the determinant way for u cross v, v cross w, and w cross u. And we see that we get these outcomes here. And then, of course, when we do the dot product for u cross vw, v cross w dot u, and w cross u dot v, we see that we get 8 each and every time for that. So this takes care of verifying that this property is true. So now we're going to move on to example 4b, which says, all right, for each set of vectors, we're going to find the volume of the parallelepiped, which is just basically find the volume of the box determined by u, v, and w. And so one of the things that we see here is that an application of using the triple scalar product is essentially trying to find the volume of a box, okay? And so here, since I already know what the triple scalar product is, all I have to do is take the absolute value of it to get the answer. And so that is what I've done here. The reason why I have these other two calculations here of the triple scalar product is just to show you the other ways that I could have arrived at the same answer. So, of course, for was u cross v dot w, that way we actually did that back in example 4a, and we got 4. We also know that to calculate the triple scalar product, we can also use it in its determinant form. And so I've shown you that if I use the determinant form here, I will still end up getting 4. And of course, since we already knew what this was from doing this calculation in 4a, I just take the absolute value of what I have left. And I know it's just absolute value of a number because this quantity here is just a real number. And I see that I get 4 in this case. And so the volume here, if I wanted to be, totally correct here, I would want to say that this is 4 cubic units. So I want to do something like this to make sure that I'm recognizing that what I am calculating is actually a volume. All right, so for example B, kind of the same thing. We write our vectors u, v, and w in component form. Again, I know what u cross v is in this sense, but I really don't need it because, again, we've already calculated what the triple scalar product for u, v, w is going to be, and we saw that it was 8. Absolute value of 8 is 8. But again, we can do this via the determinant way of doing the triple scalar product, or we can calculate it just like how we did back in example 4a. All three ways, we end up getting 8. And again, like I said before, since we are talking about a volume, we really need to answer this in cubic units. Okay. So for our last example, we're given some non-zero vectors u, v, and w, and we want to use the dot product and cross product notation as appropriate to describe the following vectors and or quantities that they want us to find here. So, of course, first is going to be the projection, the vector projection of u onto v. And of course, we learned this back when we were studying the dot product. We know the projection of u onto v is just going to be u dot v divided by the magnitude of v squared, and all of that times the vector v. And of course, we put the vector v here since the projection is on this particular vector. And that's what it is by definition. So if we want to find a vector orthogonal to u and v, another way of saying that is we want a vector that's going to be perpendicular to both of these vectors. Well, we know that the cross product pseudo vector result actually ends up being that. So by definition of what the cross product is supposed to yield you, we know that U cross V is going to be a vector that fits that description. Okay. Now, if we want a vector that's going to be orthogonal, aka perpendicular to both the pseudo vector U cross V and another vector W, then all we have to do is cross those two vectors together. Okay. So this is a vector and that is a vector. So here we just do the cross product of those two vectors and we'll get a vector that's going to be perpendicular to both this one and that one. Okay. Now, we just got through doing an example of calculating the volume of a box or a parallelepiped. And if we wanted to do that and the sides of this box would be written in terms of vectors u, v, and w, then we would essentially just do the triple scalar product and take the absolute value of it, which is what you see here. And the area of the base here is essentially going to be what U cross V is. And of course the height, we saw back earlier in this video that the height can be characterized by the magnitude of vector W times cosine theta. So if we want a vector that's going to be orthogonal to both U cross V and U cross W, again, these are two vectors. So all we have to do is do the cross product on them, and we will get a vector that meets that condition. Okay. And then lastly here, we want a vector of length, which is basically magnitude of vector U in the direction of V. And essentially, we know that since the direction of V just means a unit vector of V, which is the vector V over its magnitude, then the vector that we want here has got to have this magnitude and got to have that direction. So we just multiply those two things together, and that's the result that we get. Okay. So it'll just be the magnitude of U scalar multiplication with the unit vector of V. And so with that, this concludes the second video in this video series on cross product, where we've actually gone over what the cross product is, how it's defined, and some applications for it, and we've actually shown some examples. So the third and final video in this series, I'll actually go over some informal proofs. We really didn't use the form of the cross product with the sine theta in it, but I'm going to show you how we actually can arrive at that. And I'm also going to go over a proof that talks about how we end up with the determinant form for the cross product. All right, see you there.